So we're going to work an example of a ratio problem. And a ratio problem is one where the knowns that you're given are not numbers with units, but the knowns are given as ratios of a value compared to some other value that you know. And so the one we're going to do is a satellite problem. This is from the Knight textbook, and we're going to do problem 49. So, but before we do that, you should read this little heading here. In recent years, scientists have discovered hundreds of planets orbiting other stars. These are called exoplanets. Some of these planets are in orbits that are similar to that of Earth, which orbits the Sun at a distance called 1 astronomical unit. So an astronomical unit is a certain number of meters. So problem 49 says we have an exoplanet Kepler-42c that orbits at a very close 0.0058 astronomical units from a small star with a mass that is 0.13 that of the Sun. How long is a year on this world? So we're going to solve this problem in terms of ratios rather than putting in all the units on every number. And doing that is a useful way to know how to set up problems, because you can see how your answer two numbers.
So we're going to solve for how long is a year on this exoplanet Kepler-42c, which means we're going to be solving for the period of that, or more particularly, we're going to solve for the ratio of the period of that exoplanet compared to the period of Earth's orbit around the Sun. So I'm going to start every problem with a picture. So when we do ratio problems, we're going to be comparing two different situations: the exoplanet orbiting its star and the Earth orbiting the Sun. But the same picture applies to both. So let's just say we have a star here and a planet going around that star in a circular orbit. So that would be my picture. I'm going to go ahead and add the information for a force problem. This star is moving in a circle, so it's accelerating towards the center, and its velocity is tangent to that circle. And my coordinate system, I'm going to make positive that way. So we have a force diagram on that planet, and that force that keeps it moving in its circular orbit is the gravitational force from the star. So I'll say m of the star, m of the planet, over r squared, and r is the radius of that orbit. So for any satellite problem, we're going to do a net force equation and make that net force big G m star m planet over r squared. That is equal to the mass of the planet times the planet's acceleration. Because it's moving in a circle, I can put either v squared over r for the acceleration formula, or because speed is 2 pi r over period, another way to write that, centripetal acceleration formula, if I sub that in, is 4 pi squared r over t squared. Okay. Now, the goal is going to be to find the period of our Kepler planet. So we want to solve this algebra out for t. Well, I can do that. First of all, I can divide out the mass of the planet from both sides, and then multiply t squared to the left. So let's do that. And remember, this net force equation would apply to any planet, Kepler or the Earth, orbiting around its star. So I'll put t squared on the left. On the right, that's going to give me 4 pi squared. When I multiply r squared by r, I get r cubed, and then I have to divide all that by big G times the mass of the star. Okay. So now, I could, if I knew all the numbers with units, I could just sub in for the mass of the star and the radius of that star's orbit in meters and the big G number, and I would get the period. I could solve for the period in seconds. When we do a ratio problem, the knowns, I will go ahead and put those knowns on the next page, and we'll come back to our formula here. What we're given was that the radius of that Kepler's orbit compared to the radius of the Earth was 0.0058 AUs compared to 1 AU, which is Earth's orbital radius. So that's 0.0058, a number with no units. It's a ratio. We were also told that the mass of the Kepler star compared to the mass of Earth's star, which is the Sun, is 0.13. So we're given those ratios. So, and we showed from our formula that t squared is equal to 4 pi squared r cubed over big G times the mass of whatever star. So now when we do ratio problems, what we're going to do is apply that. We're going to solve for our unknown, and then we're going to for t. All right.
I'm going to take the square root of both sides, like that. Now I've got t isolated. So I'm going to write that equation, but I'm going to write it twice. I'm going to write it once for Kepler and once for Earth. So I'll have the t of Kepler must be 4 pi squared times the r of Kepler cubed over G times m of Kepler star. Take the square root. And the same equation applies to Earth. The period of Earth must be 4 pi squared, the radius of Earth's orbit, cubed over big G m of Earth star, which is the Sun, square root. By writing that twice, and pay attention to your subscripts so you don't lose track of whose period and whose radius you're talking about. Now we can take a ratio of both sides. That's how we set up ratio problems. So I'm going to divide the left side by the left side and the right side by the right side. And if I do that, on the left I get the period of Kepler compared to the period of Earth. And on the right side, most of these things are constants that are the same for both Kepler and Earth, so they're going to cancel out. So we have 4 pi squared, big G cancels. So this will simplify a lot. I have a fraction in the numerator divided by a fraction in the denominator, and by the rules of algebra, what that means I can do is multiply by the reciprocal of this fraction that's in the denominator. So that's what I'm going to do. And all of that's under a big square root. So what I'm going to have is r
Kepler over the mass of the Kepler star. And then from this fraction in the denominator of my ratio, I'm going to multiply by its reciprocal, which means multiply by m Sun over r Earth orbit cubed. Alright, and what you can see is now I've got my answer, which is a ratio, in terms of my knowns, which are also ratios. So I'm going to sub in now the ratio of my two star masses and the ratio of the two orbits, radii, and then I'll be done. So I'm just going to copy my formula one last time. I've got period of Kepler compared to period of Earth, which is the square root. Alright, I'm going to do this ratio first. That ratio is 0.0058, but that was the ratio of the radii. I've got to cube that. Then I'm going to multiply by this ratio, mass of Sun compared to mass of Kepler star. Well, that is 1 over 0.13. And then I sub in my numbers and take the square root, and you can try that yourself. You're going to get 0.0034 with no units, because again it is a ratio of the two periods. And so we can then finally say that the period of Kepler planet is 0.0034 times the period of the Earth. Now, if you wanted to go and put your units in at the end, you would know that the period of Earth's orbit is 1 year. So you could then find that this is 0.0034 years. And if you want to convert that to a different time unit, you can. You can convert years to days or to hours. I converted it to hours, and it turns out that the period of Kepler's orbit is only 10.7 hours. So it's going in a very tight orbit around its star, and it goes all the way around that star in only 10.7 hours, which is pretty amazing. So we have worked through a complete ratio problem. The key point is you want to set up your knowns as ratios. You want to solve your physics equation, whatever that might be, a DVAT, or in this case a net force problem. You want to solve that once for your unknown, which in this case was the period. And then you want to write your formula for what you're solving for. You want to write that formula twice, once for each of the things you're comparing. Then you take your ratios to get the ratio that you're looking for right here. And the ratio that you're looking for will be in terms of the known ratios. And then you sub in your known ratios.